Okay, today vector addition and subtraction, and let's start with talking about addition. Vector addition, when we want to add two vectors together, what we mean is the sum u plus v, that is u vector plus v vector, is the single vector that has the same overall vector, same overall effect as u and v acting separately. I'm just going to add a little something to that. I just want to make a little more information on that. Acting separately, one after the other. That's the addition part, is we're doing them one after the other. So a good analogy to think about is driving somewhere. If you travel from A to B and then from B to C, the overall effect is the journey from A to C. That's obvious. But in vector terms, what we mean then is if AB is the first part of your journey, as seen in the diagram to the right there, and BC is the second part of your journey, and you can see that in the diagram there, then the overall outcome is AC. So all we mean by that is the vector AC is equal to the vector AB plus the vector BC. So to really jump ahead in our thinking here, what we mean is we want to arrange two vectors tip to tail to come up with the sum of those two vectors. That is, the first vector, we go from the tail to the tip, that's A to B right here. And then at the end of the tip there, we put the tail of the second vector, and we go tail to tip there. And so the sum starts at the tail of the first vector and ends at the tip of the second vector. Now, we don't need all the A's and B's and C's there. We can talk about generally U's and V's by going, okay, if we have a U and a V, and they're arranged tip to tail like that, then the sum vector right down here is the U plus the V, one acting after another. And notice that the sum of two vectors is also a vector. So when we add a vector to a vector, we get a vector. And the single vector produced from the addition of two or more vectors is called the resultant. So in this one, this was the resultant. And this was the resultant. Okay, so some examples. Name a single vector equal to each combination of vectors. And if you're really following along, you don't need the picture to know what AB plus BC is going to be, but I'll show it on the picture anyways. If you do AB right there, ooh, that's too big. Let's go smaller there with the highlighter. Okay, so if we do AB right there, and then we add to that BC right there, the sum total is, in red here, right there, AC. So AC, and you can do that algebraically. That's great if you see that. If you can see that AB, BC will be AC, no problem. But the picture really shows it. AB plus BD. So and again, you can just look at the letters, and when they're like this, wonderful. If you can just look at the letters and get the answer. But if you want to see the picture of what's happening here, we're taking AB, and we're adding BD. And what will that sum be? It's the effect of going from A to D right there. That's the overall effect, and I get AD. Now, if you think this is easy, that's because the easy examples I've chosen to start off with here, where the letters all line up nicely. It doesn't always have to happen like that. But this third one, it does. AB plus BC plus CD. Maybe you can just look right at that and go, oh, that's A to D. I went from A to B, then from B to C, then from C to D. The overall effect is A to D. Very good. That's a great way to handle those. But just to see it in the picture, if I was going from A to B, and then from B to C, and then from C to D, the end result of all of that is that I went from A to D. So it's the end result. The resultant of all that is AD. Okay, so I've been using this all the way along, but just to put it in formal words, the triangle law of vector addition, to add two vectors U plus V, place the tail of the second vector at the tip of the first. The sum U plus V is the vector starting at the tail of the first vector and finishing at the tip of the second. So this one, the example says, use the triangle law of vector addition to draw the resultant of A plus B. So what I get is, here's an A, like that. Try to draw these sort of to scale, but not exactly. I'm just trying to get the idea here. And then B I'd add on to the end there. And the resultant here in red, there's what A plus B would look like. Start at the beginning of the first vector and end at the end of the second one. So in 3D now, we're trying to move towards 3D here. Just a fair warning, we're coming up on 3D here. For the given diagram, determine the vector equal to each sum. Well, again, this first one, AD, DH, I don't really need the picture to do AD plus DH. AD plus DH is just AH. But to see it in 3D, to get ready for tougher examples, we're adding AD right there to DH right there, and the resultant would be as if we went from A to H diagonally across the end there. Okay. Get rid of all that. AB plus BF plus FG. Okay, another one. Really, really straightforward. And it may seem like, oh, this is just so easy. So AB plus BF plus FG, if you go from A to B, then B to F, then F to G, answer A to G. But really just to show that off again, so that we're ready for tougher examples, because the tougher examples are coming right up here. In the picture, we'd go from A to B, then from B to F, then from F to G, and the resultant of all that is I start at A and I ended at G, just like I saw from the letters there, but that shows the picture of what's going on there. Can erase all that now. What was I in eraser mode? No, I wasn't. Okay, so erase, gone. Okay, AE plus HC. This is the first difficult one. They want to add AE to HC. So they want to go from A to E, which is right here, and then they want to add on H to C. But H to C doesn't match up tip to tail. So this is where the equal vectors definition comes in. Important moment in the lesson. H to C is way up here. And I want to add it on to A to E, but it doesn't match up tip to tail. But there's an equal vector in the picture I can use. I can instead use E to B, which is the exact same vector. It has the same length and goes in the same direction. And instead of using HC, I'll use EB, because EB is the same vector as HC. And if you don't like that, you're just going to have to get used to it. That's the way vectors work. You can use equal vectors even if they're not at the exact same spot in space. And so what I get here is AB. I don't need to draw it. I can see the letter matching up there. But if you do want to draw it, there it is right there. So let's get rid of all that stuff in the picture and try for one more example here. AD plus AE plus AB. Okay, so start with AD. Start with AD. Yeah, okay. AD, right there. Straight up. Then they want to add AE, but AE that isn't tip to tail with AD. It's not going from the end of AD and starting there, and that's what we want. We want to add two vectors. You want to end at the tip and then put the tail of your new one at the end of the tip. And so here, we can't use AE, but there's an equal vector I can use, and that equal vector is DH. Same length, same direction. So I'm going to change this question. I'm going to write it as I go here. AD plus DH, because AE and DH are the same vector. And then they want to add to that AB, and AB, it goes along the bottom here. But instead of using AB in the picture, I'll use HG. And you see when you do that, the answer becomes obvious with the algebraic version of this. You can see A to D to D to H to G. You go AG, but you can see it in the picture. I've drawn it as I've gone here. Okay, so keep that in mind. You can always replace a vector with another vector that's equal to it. The zero vector. Say you've got a situation like this, where you've got some u vector, and you're adding it to some v vector, and then you're adding that to some w vector, and you end up right back where you started. You get u plus v plus w, and you end up going nowhere when all that's over, and we call that the zero vector, when you've ended up at the same spot. There were vectors involved, but you ended up with the zero vector. Now, the zero vector has a zero magnitude, and is the only vector that doesn't have a specified direction. You can't really talk about a direction if you didn't go anywhere. And notice the sum of any vector and its opposite is the zero vector. U plus negative u is the zero vector. So if you go u, and then you add to that negative u, you get the zero vector. One other useful thing is the parallelogram law of vector addition. Sometimes useful. I mention it here because there's the very odd question where the parallelogram law is easier to work with than the triangle law of vector addition. It really is just the triangle law done from both sides. The idea is that if you want to make u plus v, you could go u plus v, like we were doing before, and go tip to tail there. So there's u plus v. U plus v drawn here. I'll highlight this in yellow. U plus v drawn u plus v. But you could also do v plus u done the other way. And what you get is a parallelogram out of all this. And so sometimes the parallelogram's easier. Now, you might look at that and think, oh, that's not easier. And you're right. In most situations, the triangle law is much easier. Just do one side of the parallelogram, a triangle on either side. But it does come up with a parallelogram law is easier. So just throw that in the back of your mind, as the parallelogram law does the same thing as the triangle law for vector addition. You can go u plus v, or you can go v plus u, and you get the same thing. Example. Here's closer to a real-life example. A boat is traveling across a river at a speed of 14 meters per second. Whoops. So straight across here, straight across the river at 14 meters per second. And at the same time, the current 5 meters per second carries the boat down the river. So that's this here, 5 meters per second. And that's a right angle because they said going down the river like that. And it says find the resultant velocity. Now, I've already set this up, all ready to do this question by making it vector addition. I put them tip to tail. I put the end of the velocity of the boat. At the end of the velocity of the boat, I put the current. So they're all set up to do vector addition here. And so my resultant of this whole situation is here. And once I draw that resultant on there, I'm ready to find the resultant velocity. All I need is a little Pythagorean theorem. Sorry, we're sliding all over the page here. To find its length. So let me switch to a different fancy color here. So if I want the length here, I'll go c squared equals 14 squared plus 5 squared. C squared equals, get my calculator out here. I get c squared equals 221. And I'll have to square root that to get its length. And I get 14.9 to 1 decimal places. 14.9 meters per second. So the result is that this boat is going to be going 14.9 meters per second. It's sped up a little bit because of the current pulling it downstream like that. Not all that much because the current wasn't adding right on to the end. It was just pulling it off course. So they wanted magnitude, but they also wanted direction. So to get the direction that's been pulled off here, I'm going to go a little tan theta equals opposite over hypotenuse. So I need the tan inverse of 5/14. So here we go, tan inverse 5/14, and I get 19.6 degrees. It's been pulled 19.6 degrees off course. So therefore, the resultant velocity is 14.9 meters per second, pulled off course. .6 degrees. Now, for you physics people, you might be like, oh, well, it would be 19.6 degrees south of east or whatever. And yeah, we'll get to all that stuff. But for now, just to get the idea of how this will work in real world situations. This is a troublesome question because textbooks and so on aren't very specific on what they mean here, and it can mess you up. So I'll be sort of careful on assignments and tests and so on to make sure I'm clear about this. But when they say this in the homework, given vectors A and B such that the angle between the two vectors is 60 degrees, they mean that when the angle between the two vectors is 60 degrees tail to tail. And they don't always say that they mean tail to tail. And we do that's what they're referring to when they say the angle between two vectors. So what I end up with is sort of a troublesome situation here, because here's the vectors A and B. And the angle between them is 60 degrees when they're tail to tail like that. But they want us to add the two vectors together. Oh, the vector symbols are missing here. Let me just put those on there. But they want us to add those two vectors. So to add those two vectors, we need them tip to tail, which means this b vector needs to be slid out. And instead of it being there, it's got to be down at the end here. And when it moves down to the end there, and I didn't keep it at the same angle there, so that's going to be weird looking. So let me just fix that up. B was sort of like this. And if this angle in here was 60, that means the angle when they're added together is actually 120. And that'll cause you a little bit of trouble when you're doing these questions because you'll have the wrong angle there. There's the resultant when we do it, and the angle between those is 120. So this is vector A was length 3, and vector B was length 2. There's the actual picture of the situation, with this being the A vector and this being the B vector, okay? So we want to find the length of A plus B. We need a little Pythagorean, or not Pythagorean theorem, a little cosine law here. So C squared equals A squared plus B squared minus 2AB cos of the angle between those two vectors. And this time, between the two vectors is between the two vectors when they're added together, tip to tail. So that changes the angle to the supplementary angle there. So I got to do 3 squared plus 2 squared minus 2 times 3 times 2 times cos of the 120 now. So I'll type that all in. 3 squared plus 2 squared minus 2 times 3 times 2 times cos 120. And I get 19. And I got to square root that. I get 4.4. So the magnitude of A plus B will be equal to 4.4. Okay, so just watch out for that little piece of information, but we'll try hard on tests and so on to make sure we mention that tail-to-tail thing, even though the homework doesn't always do that. Vector subtraction, a tough concept in a lot of ways. So you might have to watch this part of the video a couple times to make it clear, but the explanation I'm going to give will really explain what's happening, but you're just going to have to listen to it a couple of times for it to all become clear. So when considering vector subtraction, it's useful to consider the idea of subtraction in arithmetic. In arithmetic, subtraction is the inverse operation of addition. For example, 7 minus 5 equals 2. And now, hold on. Some people, when they think of 7 minus 5, think of taking away 5 from 7. And that's definitely a great way to think of what 7 minus 5 is. But the other way to think about it is actually probably the way most people thought about 7 minus 5 when they first learned about it. Is when they first learned about it, they knew their addition facts. And the idea was, when you're doing 7 minus 5, you're looking for what do I add on to 5 to end up with 7? And they go, oh, 5 plus 2 is 7. So what I added to 5 to get to 7 was 2, and the answer's 2. That is the only way to really handle vector subtraction in a geometric concept. That is, if you want to do A minus B, what you want in the picture here is the vector that goes from B to A, like that. But this time, weirdly, not tip to tail like addition. To get this all set up, because it's the inverse, it's not going to be tip to tail, it's actually going to be tail to tail when we do vector subtraction. So vector subtraction, we do tail to tail. And we're looking for the vector you add on to B to get to A. Just like here, look for the number you add to 5 to get to 7. So there's another picture of that below. Similar to arithmetic, we can also consider vector subtraction as adding the opposite, and this is a very powerful way to handle the situation, actually, as my screen jumps again on me there, is instead of thinking of A minus B, think of it as A plus negative B. That's what I'll talk about mostly here, is how you can just add the opposite to do subtracting vectors. So there's the tail-to-tail method, where you arrange them tail to tail, like I showed up there. And A minus V is the vector from the head of B to the head of A. The opposite method, where you just, instead of subtracting A minus B, you just go A plus negative B, and you'll get the same answer. Note that A minus A would be the 0 vector, and A minus A is the same as A plus negative A, which is the 0 vector. So that stuff all works like you might expect it to. And that seems weird that we're mentioning that these things work the way we would expect them to. but there's something coming way down the line, next chapter, that doesn't work the way we would expect it to, and then it'll make sense why all the way along the line here we keep making a big deal out of things that work the way we would expect them to. So don't worry about that too much for now. Just know, okay, the rules work like we think they're going to work there. So this says, for the following vectors, draw u minus v. Now, if you got to draw u minus v, the easiest way actually is to do the first method I mentioned there, which was to tail to tail and add to b to get to a. So here, tail to tail, u minus v. So if I'm going to draw this tail to tail, I'm going to draw v like that, and u like that. So now they're tail to tail, and I'm ready to do vector subtraction. And what I want, and I better change colors here. I'll switch over to like a something that's very different looking, green. If I'm doing u minus v, I want to know, what do I add to v to get to u? So I've got to add on to v to get to u, and there's my picture of u minus v. Not simple. You may have to watch that a couple of times and go back and look at 7 minus 5 a couple of times to really get that idea clear. Where was I? Oh, down here. Now, final example, it says ABCD is a parallelogram. That's important because we know then that AB and CD are parallel, and AD and BC are parallel. That's going to be important in the questions I do here to know that it's a parallelogram. It says express the following as the differences of a single vector. So it says AB minus DA. Okay, so in a situation like this, I don't have to do that tail to tail thing. I can go ahead and go after this thing and go AB, this is part A. I'm not going to do subtract DA. I'm going to do add AD. So I'm going to add the opposite. So instead of subtracting, I added, but I changed this vector DA into AD. And when I look at my picture, I want to do AB right there. I'm going to do that with the highlighter. It's just a little easier to see there. There's my highlighter. I want to do AB, but I want to add on to that AD. Well, I can't add AD because AD doesn't line up tip to tail like I would want in addition, but I can, instead of using AD, because this is a parallelogram, I'll use BC. And so what I get is AC is the answer here. And you can do the rest of the picture there, but lots of times the picture you're just using to set up the algebra, and then you go from there. So next one here, CD minus AD. So I'm going to do this similarly. I'm not going to try and set them up tail to tail like we did up here and try and draw the weird vector and everything like that. All I'm going to do here is go, okay, instead of CD minus AD, I'm going to go CD plus the opposite of AD. Sometimes people like to write add the opposite like that because that helps remind them that I want CD plus DA. And this particular question, oh, I don't even have to draw it. CD plus DA, boom, CA. And you can draw it if you want, if you think you need to, but I can see what the answer is going to be because C to D to D to A is CA. Last one, AB minus DC, same procedure. I'm going to go AB, and instead of subtracting DC, I'm going to add CD. I can't add CD because CD doesn't end up at the end of AB, so I'm going to change CD to the vector that it's equal to, which is BA. And look at this, ABBA, dancing queen. No, okay, ABBA, A to B, B to A. What I end up is back at the same spot, 0 vector. I get it. There's a few tricky concepts in that video, so go back and rewatch the parts you need to make that stuff all clear. And if not, jump onto the homework and take care of this stuff.